thì á, hả
Okay, welcome back, everyone. Let's get started. Today, we'll be talking about filtering and aggregation. We've talked a little bit about filtering already when we talked about interaction, but today we'll be looking a little bit more formally at what does it mean to filter, and then we'll spend like quite a bit of time at aggregation methods such as clustering and dimensionality reduction and so on. Okay, so first, are there any administrative questions? Everybody working hard on their project? Anything that's come up there, or? Well, if not, then let's get started. So when we talk about like filtering and aggregation, what we really want to do is, it's kind of like usually a method to deal with scale, right? So we want to filter. By filtering, we want to remove items ideally, or items or attributes ideally, by kind of like removing the items that are not relevant. And if you think about this in terms of tables, remember that you can remove both rows or columns of a table. And so you could kind of like filtering approaches or selection or query approaches to either of those. And for aggregation, you want to kind of like take items or attributes and group them in some meaningful way. So for example, if you have items that are very similar, maybe you can just represent these very similar items instead of representing all of the different items, which is something that is also very useful if you want to deal with scale. So let's start off with filtering, because that's kind of like the simpler one. And filtering is about eliminating elements or attributes. And I guess we have to ask ourselves, like, what is it that drives a filter? And the answer to that is any possible function that partitions a data set into two sets, like one of the elements that are still remaining, and then the elements that are removed from that. And you can come up with any kind of filter that you want. You can say it's bigger or smaller than x in a particular dimension. There is a fold change between two different dimensions. There is some kind of like statistical measure, such as like a noisy data or something that is insignificant, but you can come up with arbitrarily complex filtering functions. And so yeah, similarly for attributes, you can like remove attributes based on whatever you can come up with. And of course, there's visual means to create those filters. And I also want to kind of like talk a little bit about this duality between queries and filters, because I think they're very, very related, but also slightly different. Well, first, this is about coupling between an encoding and interaction so that the user can immediately see the result of an action. Remember when we had this this kind of like home finder there where we also did like an activity on where we kind of tried to redesign the filter operation. And so to come back to this query versus filter dichotomy, you should think of this as queries start with 0 and then you add in elements, whereas filters start with everything and you remove elements. So filters are great if you kind of like have like a small enough data set that you can like start with an overview, show everything at the same time, and then realize, well, some of the items are not all that relevant, and I start removing them. Whereas queries are usually especially useful if you have a really large data set where you start and where you can kind of specify what you want to look at and add in those elements. And so the classical example is a query is like a search, like a Google search, for example. And you clearly don't want to start with like an overview of all possible search results in something like query, like Google. So instead, you want to query for something very specific. So the bigger the data, the more likely you want to use a query approach first. And so this is this film finder from back in the day, like one of the early examples of filtering, where we had these kind of like menus on the right side where you could kind of say, I want to look at films that are between 16 and 270 minutes in length with Sean Connery and so on. And then you get kind of like the subset of movies that are in that set. But of course, things have changed a lot since then. And we have these kinds of interfaces all the time now. One important kind of like development is scented widgets. So like if you look back at this example here and these on these widgets here, they're not particularly smart, right? They don't tell us like, what is the consequence if I like move the slider from here to here? Am I going to remove half the data set, or is it just something that is barely noticeable? And so the idea of scented widgets is to give people a bit of an information sense to kind of see what interaction will kind of like result in. So you want to kind of like lower the cost of information foraging by giving people better cues. And so the typical example is something like an histogram you see in the top and the bottom left that is combined with a filter or selection item. So that way you can easily spot, well, if I remove this part of the data set, I am going to remove like a good chunk of the data set. Whereas if I say remove like the elements in here, then that's not going to change the number of items all that much, right? This is something that I can immediately see. And similarly, in this example here, the size of the data set is kind of encoded by color. So we have a little bit of information about how much is kind of like expected if I load this particular data set. Or you could kind of like combine user interface widgets with some kind of meta information. For example, here is like who created various, let's say, files or folders. And we can kind of visualize this directly with this more traditional file browser tree. So a good example of like a visualization system that does that is Keshev. So here, this is about medals that individual athletes won in the Olympics from 2000 and 2012. So we have like a multiple coordinated view visualization here. We have like a ranked list here in the middle. So you can see Michael Phelps won 8 medals twice in 2004 and 2008. Then we have like information about all of these different elements. And then here we have kind of like the scented widgets piece, right? So these are filters. I can say, I have an idea that like there's a lot of athletes that won exactly 1 medal, but there's very few that won 2 or more. And so I already know if I change that filter here to only include 2 or more, that I'm gonna like significantly reduce my data set, right? And I can see here is again the distribution. If I reduce this to 2 or more, I have again significantly reduced the data set. And it's also kind of like, well, this is just a note on the data. It's interesting how swimming dominates for these multi-medal athletes. But you get the idea. I have these, and this of course happens for all of these interfaces, right? Like if I'm looking at, are there any people that did this when they were over 22? I can do that, and I immediately get a sense. If I'm looking at, like now, I know that over 30 is a fairly small portion of the data set, and so I kind of have an idea of what's going to happen before I even apply the action. And you can also use, like one thing I really like is to do this with interactive legends, right? If you have something like a bubble chart, you need to visualize a legend, right? You need to show what is the size of a bubble, what does it correspond, and then you can kind of like combine this legend directly with a filtering widget. So here, for example, I could kind of like, I have these two sliders that I can kind of like drag around to exclude elements that are smaller than this and exclude elements that are bigger than this. And so I have both my legend and my interaction widget in one place, which is kind of like a super convenient way, because it's kind of like where we look at to orient ourselves. And if this is the same thing that we can use to interact, then this just helps everybody. And alternatively, this is kind of like an example for querying. So I showed this before. In this tool, like this is a very large network exploration tool, and you can put in like a name, and then you will kind of like pull up that name and their connections in a network. And that is useful here because we have networks, like this is a network with a couple of thousand, like 20 or 30,000 people and papers in there. And so like starting out with an overview and filtering it down wouldn't be all that useful. And so usually also the kinds of questions that you might ask from a data set like this are specific. Especially, well, this visualization technique supports specific question, right? Where you can say, hey, what is this person's publication records? Who are the co-authors? What are roughly the topics they work on? And so on, these kinds of questions. The other thing that I really like about queries is this idea of sketches. And so like we often have a mental map of what we expect from a data set. And sometimes it is kind of like easy to let users sketch it and then kind of draw the query. And so this isn't like necessarily data visualization, but it's like a very good example of this. This is for LaTeX symbols, which are kind of like, there's so many different symbols, right? And it's hard to remember the exact command for which symbol. And so I can just draw here. And so if I draw here, this recognizes, oh, I might have tried to do either the product or pi, or like an uppercase pi or lowercase pi. So it gives me all of these examples. Or I could draw something like this, and it might recommend infinity symbol or any of these others, including a bat. Interesting. I can try like a tilde, and it gives me the different versions that I have. And so this is a tool I frequently use myself if I'm writing and I need to find like a symbol, and I have a mental picture of it, but I don't exactly know how that symbol is called. I can just draw it, and then this will give me all of the symbols that are similar, and I can pick the right one here. For data visualization, this is like a great paper that was published at CHI a while ago for running queries in time series data. And I'll play this brief video here. So this is kind of stock prices here. You can kind of navigate this time series of stock prices. And then you can start drawing. And the system kind of like highlights all of the different places where this particular pattern appears. And you can refine like how fine-grained it should look at oscillations. And then you can also, like this is I think a heartbeat, like an electrocardiogram, and you can specify kind of like the granularity, the scale, so that like you get specific scale patterns. And this shows kind of like you can query multiple time series at the same time. Okay. Great. So this is kind of like what I wanted to say about filtering and querying. And now I'm moving on to aggregation, which is kind of like the bigger topic for today's lecture. So aggregation is about like creating a group of elements and then representing it by a typically smaller number of derived elements, either elements like items or attributes. And why do we care about aggregation? Well, remember in the Tabular data lecture, we talked a little bit about aggregation. We use these kinds of methods like histograms and box plots and violin plots and kernel density estimates to aggregate a data set and give us like a good summary piece of information about the data set. But we generally, like, aggregation is really all about scalability and being able to kind of like represent items in like, or represent like multiple items with one with kind of one representation, so that we can kind of get a good sense of what's going on without having to look at all of the different details. And if we think of aggregation in terms of space, in terms of a map, we have this modifiable areal unit problem, which is kind of like it in cartography specifically. It matters a lot to change the boundaries of the regions if we want to analyze data, if we want to bin this in some way, right? So we have kind of the same distribution of points down here, the yellow dots, and then if we, depending on which grid we put on top of this, if we want to create a heat map, it will give us dramatically different results, right? So this is kind of like a very tricky problem with like many real world implications in our daily lives, including the problem of gerrymandering. So gerrymandering is essentially like a modifiable areal unit aggregation problem, right? You kind of want to represent the opinion of a district with some kind of like summary, like essentially selecting one congressman. So you can think of this as like, I want to aggregate all the people in my district to select the person that represents their interests. And so in that sense, gerrymandering is exactly that problem. And you've probably all heard of gerrymandering, but I just want to make it explicit what this means. And like, because the system of in the US that like a congressman or somebody in a state legislature represents a specific district, and that district is kind of like not preset, but is kind of determined based on census data, you can kind of like create districts that favor a particular party over another one. So here's kind of like a nice example. If we have like a data set of 50 people, we have like 60% of them are blue, 40% of them red. If we create, like, there's many different ways we could subdivide these people. We could kind of like create a subdivision that creates these like 3 blue districts and 2 red districts, which is kind of like exactly proportional to these individual opinions. That would be one way to do it. But of course, that doesn't necessarily like work in practice if I want to have some like area in space. I could create a compact representation like the one shown here at 2, where I kind of like divide this up and give the minority, like pack the minority into all of these different bins, so that essentially in the end you have 5 blue districts and 0 red districts, and so you have kind of like a compact but unfair representation. But you can even create areas where you kind of slice it such that the minority actually gets the majority of the district. And so in this example in 3 here, we have selected a pattern, like an area that that kind of gives red 3 districts and blue districts, and overall has red win. And this is kind of like what gerrymandering is all about, right? Kind of like packing your kind of like the people that you don't want to vote for you, packing them very densely in one area. For example, give them that one area, but then slice everything else up so that you get a majority in the rest of them. And this is like done frequently by both parties. Some states now have regulations that prohibit that. Some courts have ruled that this is illegal, but this is like an old Pennsylvania map. And as you can see, the red district here is clearly not made with some kind of like compactness criterion in mind, right? This is not made so that like a congressman can represent a district that is local, that is kind of meaningful in some sense, but it is really like a district that is optimized for political gains. And so Democrats won 51% of the vote, but only 5 out of 18 House seats. I think this was probably 2014 or 2016 or something like that. This was not a recent election. In Pennsylvania, this used to be like a very problematic. Here you have kind of like a couple of different maps. Here is on the left, there would be like a roughly non-partisan map. In the middle, there would be the map that was in effect a while ago. So that was a gerrymandered map. And then you could do an even more extreme gerrymandering, right, where you essentially take the same number of votes, results in very distinct proportions between 7 to 11 and 3 to 15. And there was a kind of a court case in Pennsylvania, and we can see the effect of that. And you can see those 2 maps here very clearly. On the left, you see the Pennsylvania election results in 2016 with a heavily gerrymandered map. And you can see that Republicans won 54% of the votes, but 13 out of 18 seats due to gerrymandering. And then after the court decision, they redrew the map, and you can see that Republicans won 45% of the votes, but won only 9 out of 18 seats this time around. So they went down in vote share a little bit, but they went down a lot more in seats. And so you could argue that this is a more equitable representation. And you can also argue that this is clearly kind of like a spatially more compact representation, right? But yeah, this is kind of like a problem that doesn't only affect Pennsylvania. This, of course, also affects Utah. So on the right, you see the map that was valid until 2002. And you can see that Salt Lake City was its own congressional district. And not surprisingly, Salt Lake City was frequently represented by a Democratic candidate. But that was gerrymandered in 22, so that Salt Lake City was sliced up into 3 different districts. And now after that, it is kind of very hard for a Democratic candidate to win a vote in Utah, even though there is clearly, like, out of 4 districts, more than a quarter of the population votes Democrat. They usually, including this election, don't get a congressional representation for Utah. And so here's like the 2016 results. So you see that the outcome was 4 Republican representatives to Congress. However, like if you had a hypothetical nonpartisan map, like more or less similar to what you had in 2002, but of course, like the number of districts changed, then you would have something like this. So you would have like 1 Democrat versus 3 Republicans. And of course, this happens in all kinds of states. And so, yeah, this is a hard problem, politically complicated, but clearly taken to the extreme, gerrymandering is like nonsensical from like a political process point of view. One way to do this area subdivision is to use Voronoi diagrams. And here you kind of like assume that you have a set of locations, that you have kind of like set of center points, right, that you can put somewhere. And if you have these set of center points, then you can kind of create a Voronoi diagram that kind of like encapsulates all of the area around that particular point. So on the left, on the right here, like these points, the Voronoi diagram, this point here, like every point in this cell here is kind of closest to this point and farther away from any other point. So exactly here, the point is close to this point, whereas this point here is close to this point, right? So this is kind of like the boundary for where is the next closest center point. And this, like, first, this is support. This is like a frequently used layout approach. It is kind of like one of the layouts in D3. And here's a cool example of this is an interactive D3 map of all of the airports. And you can imagine that this is useful, right? If you're flying somewhere over the ocean or over a country, and you have some kind of engine malfunction or so, you want to find out which is the closest airport. And if you have this Voronoi diagram, you can very quickly, like, there's like an absolute deterministic way of flying to the closest airport. And so we can look at this, and we can see that, like, we have, like, over land, there's many more airports, right? So we have these, like, little bit less dense and very dense regions, kind of like similar to population distribution that we know of in the US. But then over the oceans, there's not a lot of airports. And then we can find kind of like what is the airport that is furthest away from everything. And when I played around this earlier, I think this was the airport that is the furthest away from everything. And I think this is the Easter Islands. And so, yeah, you can see that there's like this huge cell for that airport. And yeah, just like an example of how you could use Voronoi diagrams. Voronoi diagrams also have other kind of like applications, which are super useful for data visualization. So here, this is a tool that demonstrates how you could use a Voronoi diagram to, like, improve interaction in a simple scatter plot. Notice that I'm like moving my mouse around, but I'm not actually hitting these points exactly, right? I'm just roughly in their vicinity. I'm not clicking those points. It's just like automatically my selection is the point that is closest to my mouse, and that is done using a Voronoi diagram. So here's like an example where this doesn't work. But if we then integrate a Voronoi diagram like this, whenever we are on a particular cell, we can highlight that corresponding data point. And so you can do that also for like a line chart. In this example here, you can see that, like, I am navigating through these different time points on a line chart, and my mouse isn't even close to where I'm actually picking, right? See that this is a very intuitive way of selecting something, and I can actually show the Voronoi diagram here, or at least I could. There's an earlier version of this tool that I used to show that had a check mark here, which I don't see now. This is like imported to observable, but somehow the check mark seems to have been lost. Anyways, you can kind of like imagine that what's happening behind the scenes here is that we have this Voronoi tessellation. Like here you can see that, like that old version of that chart. And you can see exactly which segment of a line corresponds to which cell. OK, so now I've talked about the benefits of Voronoi diagrams and what you could use them for. Now, like, how can you create a Voronoi diagram? So it's like the first step that you do is you have to calculate a Delaunay triangulation. Like a triangulation is kind of like a division of space or of an object into little triangles, which is something that is super common in, for example, computer graphics. But a Delaunay triangulation is a triangulation where no other vertices are in a circle described by the vertices of a triangle. And so what that means is that, like, if I have like these, let's say these 3 points here, and I draw this circle around these 3 points, like that describe this, like that is described by these 3 points. There's no other vertex. Like this point here is outside, this point here is outside. Therefore, this is a Delaunay triangulation, right? If you then take take the perpendicular edges, or the Voronoi edges are then perpendicular to the triangle edges. And so if you have your Delaunay triangulation here, you can simply take the perpendicular to that through the center point, and then you get your Voronoi diagram. And so now, like, this is partially helpful, but now we also need to know how do we calculate a Delaunay triangulation. And there's a fairly simple algorithm there. You simply construct any possible triangulation, and then you test whether a triangle is Delaunay, like whether like the circle really contains only the points of your particular triangle. And so on the right side here, you see 4 points with like a potential triangulation. And you can see that this is not the Delaunay triangle. And so what you do is you flip an edge. And if you flip that edge, you produce a Delaunay triangulation, as you can see with those 2 green circles, that the circle is described by 3 points of the triangle, don't include any other points of the triangulation. And so that's how you calculate a Delaunay triangulation. Any questions about Voronoi diagram, or how to construct them, or what to use them for? Okay, so then, like, a very, very common method to aggregate is clustering. And clustering is really like, if you have some kind of like, clustering is all about grouping items. And we talked about this a little bit. Clustering is really meant to group items that are similar in some way. And clustering isn't like a hard, like doesn't have hard boundaries, but you could think of it more as like clouds of items that have some kind of similarity. And clustering isn't deterministic typically. And so it's kind of like very, very useful, but also like a little bit tricky. And you need a lot of kind of like iterations, different configurations, and human input and visualization to arrive at a good clustering. But if you have a good clustering, you can actually represent just the clusters instead, and can reason about the clusters instead of all of the individual elements. And so that has like various applications. So for example, clustering is frequently used to group in cancer research. Clustering is frequently used to group people that have all, let's say, a brain tumor. But it turns out that there's many, many different subtypes of brain tumor that respond differently to different kinds of treatments. And so you do the clustering approach to see which people are similar, which kind of like brain tumors are of a specific subtype. And just one example of where we can use clustering. So what is clustering? It's classifications of items into similar bins. And what does similar mean? Well, we use some kind of similarity measure. And there's plenty of them. There's like Euclidean distances, person correlations, Manhattan distances, Chebyshev distances, and so on. So you can come up with like all kinds of different distance measures. Depending on the data type, some might make more sense than another. And then we have 3, or let's say 4 different types of algorithms, clustering algorithms. The first one are partitional algorithms that divide a data set into a set number of bins or clusters. So like there is each data set, each point is assigned to, for example, 1 cluster, or to exactly 1, or maybe sometimes none clusters. And the question here is like, how many bins, how many clusters do I want? These are either manually set, for example, in k-means, or they're automatically determined by the clustering algorithm, for example, in affinity propagation. Whereas like contrast to partitional algorithms are hierarchical algorithms. And these kind of produce a similarity tree with a dendrogram. And then we can, this dendrogram is this similarity tree, and we can cut that dendrogram at some point to get a number of discrete clusters. But we can do that dynamically, right? So we can like easily vary the number of clusters if we even need a discrete number of clusters. So these are the two major types of clustering algorithms, and then there's two other considerations that are a little bit orthogonal to this. Well, first, there's bi-clustering methods. So like typically, you cluster either like dimensions or records or items in a tabular data set, but you can sometimes, it's useful to both cluster dimensions and records simultaneously. And that's what's called bi-clustering. That's often useful for visualization. If the dimensions, for example, don't have like a predetermined ordering or grouping, then you might want to cluster both items and dimensions simultaneously. And then there is fuzzy clustering. Fuzzy clustering is kind of like acknowledges that the world is not absolute, that there might be items that are not particularly a great fit for any cluster. And so you kind of like have more of a probabilistic assignment of each item to a cluster. And therefore, kind of you more or less allow an item to be in multiple clusters with a certain probability. And that is a kind of these are very cool algorithms and and results also in interesting visualization problems, like how can you show this membership in multiple clusters and so on. And from a visualization perspective, clustering can be used to order. So all of the items in, let's say, a heat map that are in one cluster will be put together, or for brushing. So for example, if you have like in a geometric technique, like in a scatter plot, if you want to like make brushing efficient, you could like brush clusters instead of individual items. Or of course for aggregation. So I can represent just the cluster instead of individual items. And the idea here is that the clusters themselves are more homogeneous than the whole data set. So I can kind of like represent them efficiently. I can maybe just say, hey, the mean of my cluster is this and that might be sufficient. I don't need to kind of like talk about kind of like confidence intervals or anything like that if my cluster is well defined enough. So just to like, I've shown this picture before, but here's a kind of like to show what I was talking about. This is like a heat map that is clustered and rearranged based on those clusters. And you can see, and this is bi-clustered, by the way. So you can see the patterns like here emerge very nicely. So you have certain kind of like blue clusters, red clusters, and so on. And this is a very scalable technique, as I showed before. If I did this in a parallel coordinates plot, this isn't particularly useful. And here's a visualization technique. As I said before, like these cluster, like any algorithms like clustering are very susceptible to parametrization. So we might have like number of k for k-means, for example, really influences my results, but there might be more subtle things like choosing a distance measure or like other parameters in other algorithms, or even choosing an algorithm. And so a frequent problem is to kind of like people want to evaluate the clusters, and one way to evaluate them is to compare the clusters. And so here's a technique that we built to kind of like allow this comparison of clusters. So you have two data sets that are clustered, one here, the other one here. And like first you see this rough overview of what is the content of the cluster, but then you can kind of like pull out an individual cluster, and you see that individual cluster here splits up in this different clustering algorithm here. There's like a part of that is conserved here, a part of that is in this particular cluster. So you see that the two different kind of like algorithms here produce slightly different results. And this is kind of like taking this to the extreme. So here we have like multiple dimensions, and then these are all individually clustered. And then we have a representation of one cluster, or in this case here, this is a representation of one cluster. And you see that all of these items in that cluster behave very similarly. as do the items in this cluster here, or the items in this cluster here. And so because of that, you can do like a very compact representation of each cluster, and then kind of like show relationships between those clusters with these connection lines. So now let's talk about some clustering algorithms and some of their properties. I'm sure, like, if you're a computer science student, you've heard about some of these algorithms before, but I think it's also useful to recap quickly how they work. So k-means is kind of like the most commonly used clustering algorithm, probably. And the idea of k-means is to minimize the aggregate intra-cluster distance. So you have kind of like a global minimum of like x would be your point to a centroid squared, that for all points and for all clusters. Like that's kind of like what you want to achieve. Well, this is also a measure of how internally coherent clusters are. And so the way you calculate k-means is with Lloyd's algorithm. And so your input here is a set of records and a number k, which is the number of clusters. You start out by picking k starting points as centroids. Let's say initially it doesn't matter how you pick them. You can just pick some random numbers. And while then you run like a loop while you have not met some kind of convergence criterion. For each point, you try to find the closest centroid. So the way you do this, you calculate the distance between every point and every centroid, and then assign the point to the cluster with the closest centroid. Okay, and then for each cluster, you compute a new centroid by calculating the average of all points assigned to that cluster. So like first, in every step, you find like the cluster that best represents a given point, the centroid that best represents a given point. And after that, you update your centroid. And then you repeat this until convergence. And convergence, for example, could be a criteria such as no point has changed cluster, or the distance between an old and a new centroid is below a certain threshold, or you could have something like a hard cutoff. I want at most 10 iterations, for example. So let's go through this again, more graphically. So here my squares are the data points that I want to cluster, and my circles are the centroids. And I have initialized this with 3 centroids that have been randomly picked, the red, green, and blue one. Okay. And now after the initialization, and I assign the points to the clusters, and I have these decision boundaries here in red, green, and blue. And so we see that the red square is the only one that is assigned to this 1 point. And then the green, there's a lot more green squares, and then there's like some more blue squares. And now that we have assigned these clusters, we go to the second step in the loop. We update the centroids, right? And so not surprisingly, since I have only a single point, the centroid in the red cluster, the centroid of the red cluster moves directly on top of that point. And the green point is moved down a little bit. The blue is moved in a little bit. And then now if I go into this again and I start assigning clusters, I have like a new decision boundaries. And based on these new decision boundaries, I will assign the elements to different clusters. So now we have like a second point here in the red moves into a second point, or like 2 more points move into the red cluster here. And if you were to continue this, what would happen next is probably, well, yeah, it doesn't necessarily mean that this would give you a good result, but yeah, you could continue this algorithm and you would get something that is maybe reasonable. And so here's this really cool website that illustrates this. And let's do, so here we have kind of like an example that really is like, clearly we have very well-defined clusters. And if I, let's say, pick my centroids here, I run go, and then I update, like now I've assigned the clusters. You see the decision boundaries. And then I can update the centroids. And now I can reassign points. But of course, this isn't going to like result in something more difficult. So let's do this again. But now I'm going to be like sneaky about assigning points. assigning initial centroids. And so let's see what happens. Now we have kind of like a couple of different points assigned, but now I guess in the next step we will get a pretty good result. And so this is kind of like has found a fairly stable configuration quickly. Let's see. If we look at some other, like here, this is kind of more tricky, right? Like there isn't really a lot of clusters here. So let's try what happens. So what we kind of see here is that one of the weaknesses of k-means, right? It looks like at these kind of patterns in Euclidean space here, which are not necessarily like, well, I would say that there's also not all that much useful information in that particular example. So maybe let's do something else like a smiley face here. And if I do, like we could say a human could see that we have 4 clusters here. If we do that, we will get some result, but it's not going to kind of like be what we exactly expect. So we get kind of like this division here. And clearly, this is like a pattern that k-means can't deal with all that well. OK. So far, we've kind of like used k like randomly, or I've picked it to kind of trip up the algorithm. But you can do some things that are useful to make sure that you initialize k well. One way to do this is the farthest point strategy. So the way this works is you pick a random point first and say this is your centroid. And next, you pick the point that is farthest away from that particular point. And then next, you pick another point that is farthest away from the other 2 points. And by doing that, you kind of get a sensible, often more useful initialization than you would get if you just picked points randomly. But of course, like the choosing k matters, and choosing initialization matters. And this picture here shows you 2 different examples of like how kind of like k-means can end up in local minima. So it's not like a globally deterministic algorithm. So it will kind of like the image on the right here will never resolve to the 3 clusters that we really see in this example. Whereas the image on the left, we haven't picked not enough clusters to represent that particular data set. And so the point of like initialization is hard. Even trickier is sometimes to ask question about how do I pick my k's. And the way to do this is actually like by looking at the total intra-cluster distance with different configurations. And so what happens is if you like start out with a data set like you see here on the left, you have 5 clusters. If you give if you do this with a single k, like a k of 1, then you will have a pretty high intra-cluster distance, right? Like the distance from all of the points to the centroid. And clearly, as I increase k, that number of the intra-cluster distance is going to go down, right? And so and kind of like at the maximum, if I have as many clusters of data points, the distance is 0. But as I kind of like keep increasing k, I will see the intra-cluster distance kind of go down. And so like from a k of 1 here to a k of 2 here, and then 3 here, and 4 here, and 5 here. And then something interesting happens. In most cases, you will see this kind of like knee here, this flattening. If you add new k's, then you won't see like a decrease in the total intercluster distance as quickly. And that's kind of like a sign that you've reached a good point for k. So if you're kind of like, if your intercluster distance tapers off as you increase k. And so you can actually like just visually look at this and find this knee in the data set where the intra-cluster distance suddenly tapers off and isn't quite as steep anymore to identify what is the right number of clusters. Of course, in an example like this, I can just see it, right? But you should think of this as if I have like 100 dimensions that I want to cluster, right? I can't just look at this. I have to look at something aggregate like this. Okay. So as I already mentioned, Lloyd's algorithm doesn't find a global optimum. Instead, it finds a local optimum. But one of the advantages of Lloyd's algorithm is that it is very fast. And so what people do in practice, if they have like a high stakes clustering, is they commonly run this multiple times and then pick the solution with minimum inertia. And so like this is like a very, very common thing. If you just do something like k-means clustering and like scikit-learn, for example, the default setting is that it runs it multiple times and picks the best result. That kind of gets away from this problem of local optima and random kind of initialization a little bit. And you have kind of some assumptions about the data. You kind of like, k-means works great for roughly circular clusters of roughly equal size. But any of these kinds of like more complicated data shapes, as we saw with the smiley face, or with these kind of elongated blobs or half moons, that is really tricky for k-means to make sense of. And so there's other clustering algorithm if you expect to have something like that can pick something up like that. And here's an example of an unequal cluster size where k-means is also like, you could argue that this on the points on the left here are like their own cluster, but that k-means doesn't really work all that well for that. So a different clustering algorithm that really works well for these kind of like these more esoteric shapes is DBScan. And DBScan stands for density-based spatial clustering of applications with noise. And the idea behind DBScan is that these clusters are groups of dense points. And so if a point belongs to a cluster, it should be near to lots of other points in that cluster. And so that's the idea. And so that's why, for example, like you can get these very weirdly shaped clusters like here, because all of these points are close to each. There's like always points that are close to each other. And so you build up this cloud of points that are close to each other. And then DBScan also has the notion of outliers, which k-means doesn't. And so you can say, if I have like, by having a minimum cluster size, I could treat those 2 points here, for example, as outliers. They're not close to any of the other points. They're close to each other, but I have like a minimum cluster size, and hence I'm treating them as outlier. And so the key thing about DBScan is you have to pick a parameter epsilon, which is kind of like your metric of how close 2 points have to be so that you consider them close. So if a point in a cluster is smaller, like if a point that you consider for a cluster is like closer than epsilon, then you add it to the cluster. And so this this here is kind of like the same website as I showed before. The red here kind of like visualizes the epsilon, and so I can kind of, you can see the change of epsilon as I modified its slider, and then here I have my minimum number of points. And then if I like run this, you can see how that works. It kind of like looks at, it iterates over points successively and looks at our point in my neighborhood or our points in the cluster. Is there other point in the neighborhood? And that works then for like if you, yeah, you can kind of see how it works. You simply look at every point. If there is like multiple points in the neighborhood, then you create a new cluster. So you can see that here, maybe I have kind of like picked an epsilon that wasn't all that great. I could have picked like a bigger epsilon. But now let's look at this here. This is kind of like an example where k-means would do really poorly. You see this pimpled smiley here. And if I run DBScan on that, you can see that it clearly, well, it will work its way through it. This is a little slow, but it really does work for these kinds of examples pretty well. Okay, I'm not going to wait for this to complete. You can play with this later if you want to. Okay, like the third type of clustering that I want to talk a little bit about is hierarchical clustering, because it's such an important technique. There's two types. Agglomerative clustering is about like starting each node as a cluster, like every single node is considered its own cluster, and you keep on merging. Whereas divisive clustering is you start with one cluster and keep on splitting. We'll talk about agglomerative clustering because it's the more intuitive and also more used, I think, in practice. And so here, let's suppose like what I want to cluster are the points here on the right. Okay, and so I start off, and this here is going to be my kind of like my visualization of the distances between the nodes, and I'm going to draw a dendrogram on top of this. And so we start off considering each point as its own cluster. And now we look at all of the different distances, or we look through the different elements, right? And we see that A and B are very close to each other, so we merge them to one cluster. Then we see that C and D are very close to each other, so we merge them to one cluster. And we see that C and B aren't all that close. So there's like the next closest distance is actually E and F. And so the distances here, like maybe actually E and F might be the closest. And so we can draw this as a dendrogram here, like a connection. And here we have the distance in the height. So maybe A and B is next closest. So that is a little bit higher. And then we have C and D, which is a little bit higher again. So we can see we now have essentially created 3 clusters. And we have also a metric of how good, like how close those clusters are. And now if I keep looking, let's assume that I'm looking at the centroids of these clusters. Probably the next best connection is between C, D, and E, F. And so I'm drawing like a line here between those two. But this distance is fairly big, right? So I have C, D, and E, F, and that would be something that is like pretty high here. And then finally, I have like now this here would be roughly my centroid of that cluster. And then I connect this up to AB. Okay, and that would be something like this. Great. And so now I have the similarity tree. And now I can cut this dendrogram here. For example, if I cut it here, I get my 3 distinct clusters that correspond to these close points. But I could equally, let's undo this. I could equally cut it here. And now I have like these 2 clusters here. And so that is super cool, because if I have this similarity tree, I can actually cut this dendrogram in an interactive application and let the human judge what is like a good discrete clustering based on the similarity tree that I've pre-computed. So any questions about this?
You know if the height of the tree will it always be less as you draw more and more, or could there be the second level having like a closer cluster than the first?
No,
like, is that going to determine?
That can't work, because I merge the clusters in the order of closeness, right? So I start off, oops. I start off with kind of like looking at the closest distances. And so subsequently, the distances will increase.
So I guess my follow-up question to that would be like finding the optimal cutting point. Is that just always based off of human intuition, or are there algorithms for that too?
There are algorithms. Like there's, well, first, what is fairly common is that people still say, hey, I want a number k, and then that dendrogram is positioned such that you have k clusters. But there are algorithms that try to optimize this. I'm not currently aware of like a particular paper, but I've definitely seen that around. But it's not an exact science, right? It's not easy to pick that.
Okay, thank you.
So one thing about agglomerative clustering is this linkage criteria. Remember that I in a previous example here, I have kind of like made this assumption that I'm trying to kind of like pick the center point, right? If I had these clusters here, I picked the center points here, and that was okay. But then it kind of got slightly awkward with like having a center point here. Instead of having the center point of the cluster, I could also do something like picking the closest point of a cluster. So if I had this, now instead of like connecting the center point from here to here, I could say, well, what I'm looking at, what are the two closest elements of a cluster? And I could connect B and C up here, right? Now, instead of connecting based on the centroid, I would connect on the 2 points that are the closest. Or I could connect the 2 points that are the farthest. Or I could kind of like, yeah, there's different metrics to do that which often have different results. And this is like one of the tricky problems about clustering, right? That so many algorithms have like different parameterizations, and there's not like necessarily one best approach. And so like here, like what I just drew was the minimum linkage distance, the two closest elements. I could use a maximum linkage distance where like I'm picking the elements of a cluster that are apart the furthest. I could use like an average linkage distance where I compute all pairs of distances and then use that, or I could use the centroid distance, which I did initially, which is then very similar to like in results to k-means. And so here is kind of like a demo from a tool we did a while ago for this interactive cutting of a dendrogram. So here we have like, this isn't clustered yet, so I'm gonna like run a clustering algorithm in a second. Well, it is actually clustered, but not hierarchically. So now it's unclustered. We dynamically run a clustering algorithm, both in items and in dimensions, and we end up with these kind of like deep dendrograms. And this is like a 3-level focus and context approach here. And now we can dynamically cut the dendrogram by moving that slider around and create the number of clusters, both in the items and in the dimension space. And I've also shown this before. This is hierarchical parallel coordinates, and that uses exactly that kind of like hierarchical clustering. So on the very left, you see like a data set, like a dendrogram that has not been cut, and it just shows like one cluster. But then as you increase, like you keep cutting the dendrogram deeper and deeper, you add more of those clusters. And so you start seeing more of the larger trends that are appearing here. Okay, I want to move on to a design critique, unless there's any other questions about clustering. Great. So the next topic we'll be talking about is dimensionality reduction. And so I figured we'll do like a design critique that is similar to dimensional, or that is relevant for dimensionality reduction. And so what I want you to look at is this tool here about, well, you can switch between philosophers and musicians. I usually look at musicians. And you can play with this. And yeah, I'll start out breakout groups. I don't want to kind of like talk about too much about it because I want you to talk about it. And we'll do like 5 minutes and then have a discussion about this in class. And again, you can use this as an activity for today. Let me create breakout rooms. Okay. Okay. So what do you think? Let's talk about like what first. Let's start out with the data. What is the data that we see here, and how could we get it?
I guess the data we're seeing is it's like the nodes are sort of bands, and then the links is sort of which bands influenced others based on, and so the directional links with arrows, for instance.
Yeah, exactly. And like if I told you, hey, go out and build this visualization, how could you get that data set?
This is something that I thought would be pretty tough because I feel like there's a lot of subjectivity in the nodes, like knowing which musicians influenced another. You might ask the musicians themselves to tell you, but I felt like there's a lot of varying opinions based on perception of music that would definitely influence gathering the data.
Yeah. And like a lot of bands would influence each other too. It's like, for instance, Alice in Chains versus like Soundgarden, who influences who there almost. They definitely would influence each other, but what direction?
Yeah, that's a good point. So influence is not one direct, like not just in one direction, right? You, especially if you like have a long career, you can like influence each other, which is kind of like, I'll come back to this a little bit later when we talk about the timeline view. But yeah, I'm sure we can see some of the examples. Well, yeah, it's not super easy, but yeah, like one way, maybe like anybody have an idea? If I told you you have to get this data, what could you try to do?
For the philosophers, I have an approach, which is just to use the corpora for all the philosophers and to search for keywords.
Yeah, I didn't understand the first word.
By the philosopher.
What is the first thing?
Oh, you find the corpora for all the philosophers, their works.
Yeah. Okay, yes.
Yeah.
You could kind of like analyze the primary content, right? I'm guessing like what these guys here used is more of some kind of like, well, it's actually like, you know that Google, for example, has this knowledge graph about kind of like representing various things, but you could extract something like this from Wikipedia, right? Or using some NLP, you can probably, like in the Wikipedia article about each of the bands, you can very likely find some of their influences, right? And they might not completely agree with it, but it would be like possibly a good kind of a good assumption that this is roughly useful. And so you could build up a vocabulary of different bands, retrieve the Wikipedia articles, and see who is listed as their influences. What would be kind of like a way to measure the influence of a band? Like the size of the circles here.
For the bands, I could see you can use the albums released. How many albums have they recorded over the years?
Yeah, how many albums have they recorded? Maybe how many albums have they sold?
Or then the #1 hits on chart basis.
Yeah. One very interesting measure that I saw some people at MIT develop is actually the number of art languages that a Wikipedia article has been translated to, because that's kind of like a measure of global importance, right? So I'm pretty sure there's like an article about the Beatles in virtually every single language out there. Whereas maybe there's like about Kraftwerk, it might not be in some kind of like languages that are not as frequently used, right? So you could say that global consciousness is very high about entities, persons, events that have been translated to many different languages. And so that would be kind of like a metric that you can easily transfer between philosophers or bands or even like people or like politicians or anything like that. Okay, so we talked a little bit about how the data type is visually encoded already by saying the influence is the size, but how are they positioned?
They're roughly positioned by like genre, and I'm not sure whether that's manually encoded or by like who they interacted with or who they.
Mm-hmm.
inspired?
Yeah, so that's a very good observation. I would guess that they're like actually positioned by similarity, using like a method that's called multidimensional scaling that we'll talk about, well, if we have the time in the rest of this lecture. So kind of closeless means that they're similar in some way. So we could say, well, Beatles and Rolling Stones, maybe, then we have Hendrix up here, and then Led Zeppelin is closer to Hendrix than they are, let's say, to the Stones. Yeah, well, this isn't an exact science here, right? But that's roughly the idea. And then has anybody had a chance to look at this view here? What's the positioning here?
Well, it's a nonlinear scale, but it's a sort of position as a function of time.
Exactly. So we have time as because like for all of these entities, of course, time matters. Here we also see like an interesting effect that a band influenced bands that were founded before they were founded, which kind of like usually, well, I would interpret this as this band kind of like kept going until after the Beatles were still in existence, right? And you see that the influences come from mostly before the band, but we might find some kind of example somewhere here. There isn't really a great example that shows a band that was influenced afterwards. Anyways, we can, the nonlinear scale is a little bit better illustrated here among the philosophers, right? So you have like philosophy, there was like it was a big deal back in Greece. And so you see that you have like let's say, a shorter timeline here with these lines that correspond to like regular intervals, but then not a lot that happened in kind of like medieval periods, right? And then suddenly around 1900, we have very like detailed record about many different philosophers, even like 1800 or 1700, so that like more than like 3/4 of the space here is given to philosophers that have been active or born after 1700. And so this is kind of like this, by showing these lines here, we get this good sense of that time doesn't pass linearly on that scale here, which I find kind of intriguing. So any thoughts? Do you like or dislike this visualization?
I'm a fan. It seems to get the point across what they're trying to convey.
Yeah, it gets the point across. I also personally, I like this group. This is Mara and Dirk from Berlin. They're all about like visualizing, let's say, not necessarily hard data, numerical data, right? They care about these social constructs, about this kind of like casual analysis of data for enjoyment, which is kind of like for a data set like this, there isn't really any hard facts, right? Like, but it is kind of really cool to explore a data set like that, and you have like this nice detail on demand features where they give you a little bit of a summary, and you see how all of this interacts. So I'm personally very partial to this visualization and to the work that we see here. Any other thoughts?
I also think it was a very clean design, so it's easy to navigate and it's always clear what to do, and kind of helps to declutter information as well.
Exactly, it's a very clean design, and like one piece where this clearly shows is right. They didn't try to show you all of the edges simultaneously. If they tried to show all of these influences with every between all of the different bands or musicians, it would be almost impossible. It would just be like one big hairball, right? They instead chose to use this projection and only show you the edges and even the labels on hover. And so that's a way of keeping this like a fairly big data set in terms of connectivity manageable, which is very elegant here. Okay, so I'll talk about dimensionality reduction. There's only a couple of slides, so I'll not go over today, and I'll just talk about this next Tuesday. And I wish everybody a a great break and a good Thanksgiving. So thanks everybody for being here.
Thank you. Happy Thanksgiving.
Happy Thanksgiving.
Thanks. See you.